Okay, let's get started then. So it's my great pleasure to introduce today's speaker, Henry Lamb. Henry's a professor at Columbia's Industrial Engineering and Operations Research Department. His work is really at a very interesting and relevant intersection of simulation, optimization, data-driven decision-making, and I would have said uncertainty quantification, but Henry has upped the ante. It is uncertainty and risk quantification, according to his bio, so that's a new one. He's won many prizes over the years, including an NSF Career Award, a JP Morgan Chase Faculty Award, and several others. He's on several prestigious editorial boards, and his PhD was originally in statistics from Harvard, and he's been doing just really outstanding cutting-edge work at the intersection of statistics and optimization, really leading the way for kind of new directions there. And on top of that, it's been my great pleasure to know Henry for many years now, since we were both kind of in our PhDs, and he's just all around also just a great guy. So it's a great pleasure. Please take it away, Henry.
Thank you, Dave. This is the greatest introduction I've ever heard.
There you go.
And
yeah, I'm going to pay it back by asking hundreds of really annoying questions that'll derail everything.
Yep, certainly welcome. Yeah, so thank you, Dave. Thank you, Shane, and others for the very kind invitation. Great pleasure to be able to come and speak. So today I want to talk about. So in the title, I have the word trip here, and I have the word fast. So I'm going to explain both of this during my talk. But on a high level, this talk, so for those of you who have known Bootstrap, this is a statistical technique. But what I'm interested in perhaps is not only statistical problems, but simulation problems that I'm sort of more familiar with, that actually ultimately motivate this work. Okay, so so just on a very high level, what I'm interested in is doing some uncertainty quantification or some inference on some target statistical quantity. So you can think of this quantity as trying to estimate the moment or the quantile of a distribution. You look at regression, you want to estimate the regression coefficients, or in modern applications, maybe you have a machine learning model that used to do a prediction, and then you want to do some uncertainty quantification on how reliable is that prediction. And as I said, I'm most familiar with the simulation world. So in simulation, there are a lot of problems where you just want to use simulator to estimate some performance measure. And so you want to do inference on that. So there are definitely many approaches out there that you can use. But one of the approach that is widely popular is the Bootstrap. It is a resampling method, and I'll explain what that means for those of you who might not know this. And so the main sort of topic of the talk is I want to propose a way to make Bootstrap computationally cheaper. So of course, first of all, I have to explain to you what is a Bootstrap and what is the computation cost for that. Okay? And so it makes sense to talk about how to reduce that. Okay? Yeah, so let me first just spend a few minutes, just make sure that the notations are well set and everyone knows what is a Bootstrap. So suppose I want to estimate a quantity that I call psi. So this psi, as I said earlier, it could be just the moment, quantile, or regression coefficient, but also it could be other things. So you should view this psi as a function of the data distribution. Okay, so I call the data distribution P. And suppose you don't know what is this psi, but you only have a bunch of data, let's say n data points. Then this n data points will give you not P, but a p hat, right? Some empirical distribution, which is an estimate of P. Yeah, and so what I want to do, what I mean by inference or uncertainty quantification, one way to view this is just to construct a confidence interval for the true value of psi. Okay? And that just means you want to find an L and a U such that it covers the true value of psi with a certain confidence or probability. So typically this alpha would be like 5%. So that's the setup. Now, so what is a bootstrap? So bootstrap, the main principle is it relies on an observation that the distribution of a statistic can be approximated by the resample version of that. Okay, so what does that mean? So suppose now I have data and data points, and I construct this empirical distribution p hat. Okay. So a very natural point estimate for the true value of psi is just to plug in this p hat into this psi function. Okay. So this is a random quantity. Psi p hat is a random quantity, so it has a distribution. This is usually called the sampling distribution. And so resample means the following. So suppose I have a data set that I call it x1 up to xn. And what I do is I sample with replacement n times to get this x1 star up to xn star. Okay. So this x1 star and up to xn star is the same size of data set as the original data set, but it's not the same in the sense that some of these x could overlap with each other, right? Because I sample with replacement. Okay. So, so this new data set that I call x1 star up to xn star, I could use it to construct a new empirical distribution that I call p star, and I plug into the psi function again. That will give me the resample estimate. And so, the main principle of Bootstrap is these two things: the distribution of the point estimate and the distribution of the resample estimates are very close to each other in some sense. Okay, so precisely how can I write it in a more probabilistic language? So if I call this side of p hat as psi hat because I'm lazy, I will start using shorthand. So typically under some regularity conditions, we know that psi hat will satisfy some central limit theorem. So psi hat minus the true value of psi, if you scale it by square root of n, it will be approximatable by a normal distribution with some variance sigma squared. Now, if you do the resample estimate, okay, so I call this resample estimate psi star. Okay, psi star is just psi applied on p star. Under, again, some regularity conditions, you can also show that psi star minus psi hat, if you scale it by square root of n, it would be approximated by exactly the same normal distribution. So what does that mean? That really means bootstrap is just, basically you look at the original central limit theorem, and you replace the p with p hat. So then the psi true would become psi hat. And then p hat, there's a p hat inside the psi hat there. And you replace by the hat version of that, and that would become the p star. Okay, so bootstrap is really just replacing what you don't know with now the empirical version which you know. Okay, so just by this, this similarity in the limit, we can exploit that by looking at the probability of, the psi hat minus psi true lying in an interval, and that would be approximately the same as the probability of psi star minus psi hat lying in the same interval. Okay. Now, the good thing about this equality is on the right-hand side, everything is actually computable. Okay. You know what is psi hat from your data, and you could actually run Monte Carlo to get your psi star. Okay. So you can generate this psi star many times, and you can estimate the quantile. So you could get this, I call this the Q star. They are the estimated quantile from the right-hand side. And from there, you plug it back to the left-hand side. And that will give you a confidence interval for the true value of psi. Okay, so I hope Bootstrap is, and this is called the basic Bootstrap in the literature. And in fact, you can do the same thing, but using another approach. Okay? You can actually use the normal distribution directly. Okay? So you can actually, so suppose you want to just use the normal distribution and the normal critical value to set your confidence interval using the first CLT, the first central limit theorem, then the unknown parameter there would be the sigma. Okay? So what you do is, the sigma is the variance of the point estimator psi hat, but you don't know how to calculate it. So what you do is you do a resample version of that. You can estimate the variance of psi hat by the variance of psi star, and because the distribution of psi star and psi hat are very close to each other, so these variants are approximately equal. And in the literature, this is called the standard error bootstrap. Okay, so Bootstrap is, it's very easy to use, as you can see. I basically tell you what is Bootstrap, and you can apply to many problems. And it also actually have a lot of advantages. You can actually show that it is more accurate than other methods for some particular problems. But one thing that that perhaps is a drawback of Bootstrap is it requires a lot of Monte Carlo computation. You need to generate a lot of this resample estimate and do the same model fitting again and again. And so in modern applications, if you look at a large-scale problems, like for example, if the psi is actually the predictor coming from a neural network, if you want to run a Bootstrap on it, that means you need to retrain the neural network many and many times. So not sure if this is that feasible. And secondly, there is a question of how many resamples you need to draw so that your estimator or your confidence interval is accurate enough. So there's a Monte Carlo replication size B that, there are some guidelines available in the literature, but for specific problems, it can be like a trial and error process. Okay, so as I mentioned in the beginning of this talk, as I mentioned that the motivation actually comes not only for statistical problems, but in simulation problems. So here's one such example where Bootstrap is actually very hard to use. I call this a nested sampling problem, which means if you try to do Bootstrap, you would actually have to run multiple layers of Monte Carlo sampling. So the computation cost is very expensive. So in the simulation literature, there's a problem called input uncertainty that is, I think by now very well known. So what it means is usually when you run a simulation model, there's a set of input parameters that you have to calibrate. So suppose these input parameters have to be calibrated from some external data source. Okay. Then when you run the simulation, the statistical noise of this external data will propagate in the simulation model to your output. And this is in addition to the Monte Carlo simulation noise from the simulation model itself. Okay. So there are actually two sources of noise in the whole process. Okay. So for example, let's say this psi is a performance measure of a queuing model, right? Then in this case, the input into this psi function, you can think of this as the inter-arrival time distribution and the service time distribution. And so once you have the inter-arrival time and service time distribution, you plug into your simulator, and it can be used to estimate, for example, the expected wait time. Okay, so now suppose you have this external data source that you use to calibrate this inter-arrival time and service times. And on top of that, you need to run your simulator, okay, in order to get the expected waiting time. Then in the whole process, you would have two heads in this estimation, where the first head on top of the P means the statistical noise from the external data. And then the head above the psi would be the noise coming from the Monte Carlo simulator. Okay? So now suppose you want to use a bootstrap to do inference on this performance measure. Then what you have to do is first, you need to resample the P star, the input distribution. So you resample many input distributions. And then for each input distribution, you need to also run your simulator many times. Okay? So you have an outer resampling on the input distribution, and then an inner simulation run per resampled input distribution. And it gives you a total complexity of basically the outer layer sampling B times the inner simulation size R. And both of them have to be large enough for some type of asymptotic to hold. And so this could be a very big number in terms of the total amount of simulation runs that you have to make. And in fact, I should say that the problem is actually a little more complicated than this. In fact, what happens is in this kind of problems, if you look at the overall variance, the variance would have a component that is about the input simulation noise, the input data noise. And then there's another part that is about the simulator's Monte Carlo noise. And these two noises are sort of convoluted with each other. And what happens is, because of this complication, at the end, when you try to get some sort of lower complexity bound on the total number of simulations you have to run, it would be depending significantly on the input data size itself. So that means the choice of B and R not only has to be big, but also have to be carefully chosen as a function of the input data size N itself. So it's a little subtle on how to do this. And I should say this phenomenon, it really does not happen not only for like a stochastic simulation task that I mentioned now, but basically any problems where you have some noise coming from the data, and you have some other noise coming from your computation process. And so in this situation, when you do a bootstrap, you would have these two-layer sampling going on.
So, Henrik,
Yeah.
so in this case, you probably need to worry not only about the variance, you only need to worry about the bias, right? Your simulator probably would not be unbiased here.
Yeah, that's a good point. At least theoretically, you can show that the bias is of a smaller order than the variance. Yeah, but in practice, that might not mean that much. So so in this, some researchers in the simulation community, they do try to estimate this bias as well. Okay. Yeah, so this is another example where this kind of nested sampling happens. So what I mean by deep ensemble here means when you try to use neural network to do a prediction, it has been suggested in the literature that you not only use one neural network, but you train the neural network multiple times. Each time you use a random seed. Okay? The random seed can be used to control, for example, the initialization of the weights in the neural network. And then at the end, after you train all these neural network, you take the average of them. And that would be called an ensemble predictor. And it has been shown that this is sort of, it gives better prediction. Okay? So once again, if you consider trying to do an inference or uncertainty quantification of the output of a deep ensemble, okay, then you would have to run this, and if you use Bootstrap, you would have to run 2 layers, where the first layer is the resample, and then the second layer would be, how many numbers of neural network you have to train in the ensemble. And I should also mention the same thing happens for so-called bagging predictor. In a bagging predictor, what you do is instead of repeating the randomness in the initialization, you first resample the data itself, and then from the resample data, you build some base learner, like a tree or something, and at the end, you take the average to form something like a forest. So in this situation, once again, the prediction would take the form of the average of many things, and then when you want to do a bootstrap on the bagging predictor, you would have this 2-layer sampling problem that arises. Okay, so I won't bore you with too many such examples, but I could go on with 2 others. The first one is, what if you want to assess the error of a bootstrap estimator itself? Then it's like a bootstrap on a bootstrap. So once again, you have multiple layers of sampling, and there's also some results about using bagging to form bound for stochastic optimization, which runs in your simulation. Okay. So my point is there are a range of problems where these multiple layers of sampling arise when you try to use a bootstrap. Okay, so given all these complications, the main question I want to answer in this talk is, can we actually run Bootstrap with very few resamples? And well, since I'm giving this talk, the answer is a yes. Okay, so let me just qualify that yes. And the good news is, under, in fact, almost the same type of regularity conditions as a textbook in statistics would assume for a standard bootstrap, this is true. Okay. But there's a price to pay. Okay. And I will tell you exactly what's this price. So let's focus on the basic case where I just want to do inference on this psi. Okay. And psi is a function of the data distribution. And let's say psi is known. So it's not a 2-layer sampling problem. It's just the standard problem where I know what is psi, but I don't know p. Okay. So what I want to propose in the following is a method that can use a number of resamples b that could be as low as just 1. So in terms of computation cost, the Monte Carlo replication size, this is the lowest possible we can do. Okay. So here's what you can do. Okay. So first of all, you have a point estimate psi hat, and you have b resample estimates. I call this psi star 1, psi star 2 up to psi star b. And then I construct an interval that looks, somewhat like a T interval, right, that we see in elementary statistics class. So in this interval, first of all, the center of this interval is psi hat, just the point estimate. And the S is something that looks like the variance estimator of the resample estimate. But I just want to point you to maybe an observation that, first of all, inside the square of this variance formula, the center part is actually psi hat, okay, not the average of the resample estimate. And in the denominator is dividing by b, not b minus 1, not the sample variance formula that we see in the textbook. Okay. And in the t critical value, okay, so this t is the 1 minus alpha over 2 quantile of a t distribution. But the degree of freedom is the computation effort b. It's the number of resamples. So for instance, if you take b equals to 1, then the S will simply reduce to the absolute value of psi star minus psi hat. And the degree of freedom in the t critical value will be just 1. Okay, so the thing is this really a familiar interval or not really? Okay. So when b is very big, then we know that the t distribution with degree of freedom b is approximately a normal distribution. So actually, if you compare the formula that I showed you before to the formula for the standard error bootstrap that I showed you at the beginning of the lecture, they are basically the same when b is infinity. Okay? However, the point here is the b does not have to be big. Okay? In fact, you can actually write a theorem that says that for any b, any integer b, under, I haven't quite told you what are the assumptions, but I can tell you that this is a very standard assumption that people make in just arguing standard bootstrap. The confidence interval that I showed you in the last slide is asymptotically exact when the number of data n grows to infinity. And just for convenience, I call this a cheap bootstrap procedure. It's cheap because you need very few computation effort, but it's also cheap in the sense that there's a price to pay, which I'm going to show you. Okay. But this is the basic guarantee that you would get from that simple interval that I showed you in the last slide. And turns out the proof is actually not the same as the bootstrap principle that I showed you before. These are different proofs. Okay, so before I tell you why it works and all these things, maybe I can just show you some numerical results. So this is just a problem about constructing a 95% confidence interval for some percentile of an exponential distribution. Okay, so very easy, but the point is we have to see the numbers here. You have, so I'm comparing, my cheap bootstrap with, a few other candidates. So I have already told you what is the basic bootstrap and what is the standard error bootstrap. The percentile bootstrap is a variation of the basic bootstrap that also use the quantile of a distribution to set the confidence interval limit. But it exploits the symmetry of the asymptotic distribution. So for each method, I try different number of b replication size. So you can see that when b is 1, when you use a quantile-based approach, it would output you nothing because with one sample, you cannot output two numbers. Okay? So you just simply cannot get two quantiles. And similarly, if you use the standard error bootstrap in the standard error estimator, you have b minus 1 in the denominator, so it doesn't give you anything. When b is 2, it's better, but still the numbers does not make sense for all the other bootstrap methods. And when you increase b from 1 and 2 to 50, okay, then things start making sense for other methods. Now, if you look at the cheap bootstrap procedure, the coverage is actually always pretty good. Okay. Starting from b equals to 1, the coverage is already 92%. Now, the price is when b is very low. If you look at the half width of the confidence interval, then it's pretty long. Okay. So you can see that the cheap bootstrap, when b is 1, it's probably not a good thing to do. But also the good news is when b goes down to, let's say 5, it's actually not too bad. And then when b is 10, it's getting even better. So only when b is very small that this half width is a little crazy. Okay, so I don't want to bore you with more similar examples, but I'm just trying out the same thing, but a different problem. Like for instance, here is about estimating the variance. And the input distribution could be a folded normal. That just means you take the absolute value of a normal distribution, or it could be a double exponential. So some distribution is not standard. And then you compare all these methods again, and we observe basically the same pattern. Okay, so for cheap bootstrap, the coverage is always good. But for all the other methods, when B is very low, it's just not working.
Can you define coverage once, just so that we're on the same page? So what is empirical coverage?
Sorry. Yeah, so empirical coverage just means I rerun the experiments 1,000 times, and then I count the proportion of times where the interval covers the ground truth.
I see, but it's not calibration.
It's not. So empirical coverage is just a way to find the coverage. Because the coverage, I don't know what's the ground truth in this. The coverage does not have an analytical formula. So I need to.
Maybe as a slightly as a strawman argument, if I always output the entire set, that has 100% coverage. So yeah, some are going to convince us this is a much.
Yeah, I see your point. Yeah, that's a good point. So indeed, so you could always flip a coin with 95% chance. The coin would output you an interval that is from minus infinity to infinity. And then with 5% chance, you output 0, right? That's the interval. So that would give you a valid confidence interval. That's a good point. So that's why the price to pay is something important that I want to highlight. The width of the confidence interval, and also in terms of the mean and the standard deviation, is important to consider. Okay. So my point is, when B is like 4 to 5, they are reasonable in terms of the width, mean, and standard deviation. Okay. Okay. This is basically same type of experiments, but this time I'm running it on estimating the coefficient of a linear regression. The regression has 100 dimensions. Data size is 10 to the power 5th. And okay, instead of drawing a table, maybe I draw the graph. The first graph is to compare the coverage of a cheap bootstrap with a basic bootstrap. And you can see that the coverage is always like a horizontal line. But for the basic bootstrap, it will be bad at the beginning, and then you gradually catch up. In terms of the mean confidence interval width, cheap bootstrap is going to give you something bad at the beginning, but it actually drops fairly quickly. And similarly for the standard error, for the standard deviation of the cheap bootstrap.
Henry, what's up with the dog legs in the plot for the cheap bootstrap? Sorry, for the standard bootstrap.
What is the drop there? Yeah, good question. Because when I run the basic bootstrap, I use the quantile estimator, and it's a discontinuous thing. So yeah, that 40 is the time when there's a discontinuity. Yeah. I could have used other type of smoothing to make it better. Okay, so why does it work? Yes.
Can you go back to the statement
Yeah.
of the theorem?
Yes.
So what does the theorem exactly say? It says that with probability 1 and then goes to infinity, the coverage probability converges to the terminal one? Sort of, is that?
Yeah, exactly. So if you consider the probability of the ground truth lying into that cheap bootstrap confidence interval, it will converge to the 95% your target.
With probability 1?
With no, not with probability 1. It's okay. So actually, that's a good point. This is not a conditional statement. So the probability of, when I say the probability of the ground truth lying in the interval, this is unconditional.
This is
Unconditional.
Okay.
Yes.
Any here, Henry?
Yeah.
All of your data is coming IID from B, and it's the number of draws. Like it has to be IID.
Yes. In this set, yes. However, you can actually, I think you can generalize it to non-IID. Yeah.
Henry,
Yes.
on this table, so you have 2 quantities, right? The coverage probability and then also the width of this confound interval.
Yeah.
So your theorem covers both or just one? Your
So
theorem.
that theorem is about only the coverage.
Okay, so you didn't say anything about that.
I didn't say anything about the mean and standard deviation of the interval width yet.
Okay, you're going to talk about it, or what?
But yes, I will.
Okay.
Yeah. In fact, all this, the answer might be clear if I tell you how it works. And in fact, the argument is very simple. So the standard bootstrap principle says that I look at the resample estimator. It satisfies a central limit theorem. That normal distribution in the limit is the same limit as if you use, the point estimate itself. Now, in fact, just using this, you can actually show that the resample estimator, so psi star minus psi hat, and the point estimator, psi hat minus psi true, are asymptotically aligned. So just by this fact, that means if I have one resample psi star, it already provides some information about the psi hat. So I can exploit this in an efficient way to constrain an interval.
Why do you say IID? I mean, these two things are independent?
They're asymptotically independent, yes.
When n is large?
When n is large, yeah. So asymptotically means as you increase the data size.
That the theorem says that? I mean, from the previous, right? That's additional one, right? You say this implies that?
Yeah, this implies that.
The fact they have same limits, meaning they are independent?
So you can, I'm just thinking about, I think yes. And so what I want to do is, I'm going to I have a note about what is the standard assumptions you need to make. But the assumption is basically just on guaranteeing that the first part of this slide holds. And if this is true, you can actually show the other piece.
Okay.
Yes. I think, so from the first half of the slide to the second half, there is no additional thing you need to make. No additional assumption.
But it follows from the fact that that convergence holds conditionally along.
Yes.
Yeah.
Yes, exactly. This conditional on p hat is extremely important in the proof. Yes.
Uh-huh.
Yes.
So, like, would something like this hold for any kind of good empirical estimate of the variance, or no? Is there something special about that? It was kind of this particular setup. Like, I'm not. Yeah, just as far as kind of generally confidence interval theory or whatnot.
Yeah. So maybe your question is, can I just maybe try to estimate the variance? Right?
Or is this implicit? Like, I didn't look at, or I mean, I'd have to go back and see what exactly is the formula you're using. I saw some kind of variancy looking thing
Right.
using the bootstraps, and I guess I'm just trying to understand in my head, like, to what extent is there, is this a meta principle that implicitly this is using bootstrap to get some kind of estimate for the variance, and so broadly, as long as you have any kind of asymptotically accurate estimate for the variance, some kind of t-statistic-like thing must be true? Or is there something, fundamentally, is there something different that's driving this phenomena?
This has nothing to do with that foundation. This is just true for the pointer scan.
Okay.
So I have a feeling that your question is,
Yeah, maybe
very
it's-
philosophical. So
Okay.
and I was trying to put together a good
What
answer,
I
but
what I
it's,
meant. Okay, fair enough. Fair enough.
Fair enough.
I have one. So,
yeah.
all right, so at the beginning, you gave us this B and you gave us this R.
Uh-huh.
So suppose I fix this to be like I have a budget.
Yeah.
I have some BR budget.
Yeah.
Are you telling me that I can fix B to be 1 and I totally get to use as many R's as I want? Or perhaps maybe you'll tell us later that maybe it's better for me to fix B equals 2 and I should use R over 2.
Yeah, that's
I'm trying to figure out what's
right.
the best thing to do.
Yeah, so that's actually a very good question. And the thing is, what I'm showing you here is a situation where you don't have the R. You don't need the R because the psi function.
This I get.
Yeah. So when you have the R, when the psi function itself has to be estimated from another layer of simulation, the confidence interval is a little more complicated than what I showed. So I'll actually get to that later.
Sure.
But on the question of what is the optimal choice of B and R, how do you allocate the budget, we haven't done that yet. Yeah, so once you know that they are asymptotically IID, one way to exploit this is you construct a T statistic. So in the numerator, you put psi hat minus psi true. In the denominator, you put the standard deviation of the resample estimator. And so basically the numerator would be asymptotically a normal random variable. And then the denominator would be a chi-square random variable. And they are independent. So elementary statistics tells us that this is going to be a T random variable. And that's it. That's the whole procedure. And so you just invert this T statistic and you get that interval. So to summarize, basically what I do is instead of using the approximation of resample distribution for the sampling distribution, I'm going to exploit the asymptotic independence and the normality of the resample and point estimate to construct it. And it's the standard condition, right? So what you get, basically in order to get the guarantee for a standard bootstrap, you need the psi function to be, Hadamard differentiable, and the derivative has to be non-degenerate in some sense. And so the same condition is required for the cheap bootstrap too. Okay, so now that we know that, in fact, the cheap bootstrap interval comes from a T statistic, then analyzing the mean and variance of the interval becomes possible. It's basically following the same behavior as a T statistic. So when you look at the interval of a T statistic, typically the mean, you can actually derive an exact formula for the mean. And you can also derive the standard deviation for the interval width. I think in this table, maybe the third column is the most revealing. The third column tells you, which is the mean inflation relative to B infinity. It's sort of the mean of the confidence interval width compared to when you use B equals to infinity. So for instance, if you look at a replication size B equals to 5, that tells you that it's around 25% longer than what you would have achieved in terms of the mean width when B is infinite. So one can debate whether 25% is a large inflation, but from my perspective, is acceptable, maybe. Yeah.
But this, I think, the third column is a little bit misleading, in the sense that if you change alpha from 5% to 7% or 3%, it will be a huge difference.
Yeah, that's a very good point.
Because the T distribution has heavy tails, right?
Yeah.
So I like the Gaussian one,
Yeah,
the limit.
yeah.
So if you change alpha a bit, it would be huge, huge difference.
Yeah, that's a very good point. Yeah, so I had this, maybe I'm just instantly, as an instinct, I use 95% confidence interval. I show this table. But yes, if you use other alpha, it could make a huge difference. So in that case, I think maybe a good choice of B has to be revised here. Yeah. Okay, so I think this goes to Jamal's question. So what if you actually have two heads in your point estimate? So this is the standard way that I showed you before. What you do is there's two layers of sampling. You first resample, and then you do this the inner layer of simulation. But if you use the cheap bootstrap, you could actually use just b equals to 1. So this is a slide that just tries to show how cheap bootstrap compare to other things I know in the literature. Okay, so for this input uncertainty problem, there are actually a range of techniques on using different types of bootstrap to get a good confidence interval. So for instance, in the suggestion of using percentile bootstrap, you would choose b equals to 100 and r equals to 300. But if you use a cheap bootstrap, you can take, for instance, b equals to 5, suppose 95% confidence interval. And r is whatever number you use for your point estimate. So it turns out, in this case, here's one way to construct a confidence interval. So everything is similar to before, except that the critical value Q has to be revised. It's not a T, just a simple T critical value anymore. It's actually a Q that needs to solve, some sort of optimization problem where it involves optimizing. It basically involves finding the quantile of a distribution, and that distribution has several random variables inside. So I won't go into the detail of how to derive this, but I can tell you on a high level where this comes from. So basically, if you don't have the two-layer noise, okay, if you just have the one layer, then this is what we have, what I have argued before, right? So there's asymptotic independence and identical distribution among the resample and the point estimate. Now suppose you actually have the two heads, okay? Then turns out in the limit, you have to take care of these multiple sources of noise. Okay? So each head will give you a different normal random variable in the limit. Okay? And there's a coefficient in front of all these all these standard normal random variables. And so the interval that I introduced you before is, some careful way to cancel out all these unknown sigma and tau parameters.
Henry,
Yeah.
are you going to sort of discuss where these in-4s and in-3s come from? So I'll just be quiet.
Which one? The
in-4 and in-3, because I wanted to ask about something here. But I wanted to ask if you're going to embellish.
Well, you could ask.
Okay,
I'm happy to.
sorry.
Yeah.
Previously, it was important that you got some nice independence between these two, and now you don't, even asymptotically.
Yes, they are not asymptotically independent.
Right.
That's actually a very good catch. And so it's not easy to cancel out.
But that's the whole point behind the optimization.
That's why there's this ugly thing going on. And I should say there are actually multiple ways to sort of handle this. So the previous slide is just one way. In the paper, they said there's another way that I could also do it. But yeah, it's going to be more complicated than the basic version of this.
Which way do you recommend? Because I care about this because we have exactly this problem with a library, or his problems with Google.
Yeah, so the thing is, the way that I prefer, well, first of all, it actually depends on B, to Kennedy's point. So I think what we find is when B is 1, the interval that I show you is better because actually the other interval is just extremely bad in 1, B equals to 1. But when B is a little higher, then the other interval that we have is actually better. In fact, how much time do I have?
7 minutes.
Okay. Okay. So actually, in that case, maybe I would just spend the remaining minutes on just a few remarks I want to make. So the first thing is, in fact, to analyze the standard bootstrap procedures, in addition to the asymptotic theory, there's also a whole theory on how to get higher order coverage error using address expansions. Now, you can actually do the same thing for cheap bootstrap, except that now the limit is not a Gaussian limit anymore. It's a T-limit. So at least to our best knowledge, I don't think there's a literature on that. So what we try to do is first we build a theory for doing address expansion on a T statistic, and then apply this on the cheap bootstrap. And so what you can show is something that would look like this. So if you consider the coverage probability, that would be your target coverage plus something of order 1 over n, and some remaining order term. And that coefficient is going to be very ugly. It's some high, like some integral that is basically b plus 1 dimension. So if you take b to be 2, then this is like a 3-dimensional integral. So you can't really, at least I don't know how to analyze this, but you could simulate if you want. Now, another thing I want to say is, actually in simulation, there's another class of methods called batching that also utilize a t-statistic. So what this method does is it divides the data into a few batches, and for each batch, you construct a point estimate. And then at the end, you group them together, okay, to form an interval. So you could actually apply this address expansion on t-statistic onto a batching scheme as well. And it would have a different coefficient. So I don't know which coefficient is larger because it involves high-dimensional integral. But at least in terms of, there's actually a constant in front of that integral. And in the cheap bootstrap, that constant is the number of resample you use. Whereas in the batching scheme, this number turns out to be the number of batches squared. So it's a little believable that probably when B is large or K is large, the resample, the cheap bootstrap is better than a batching, which is, it makes sense on an intuitive level because when you resample, I think the number of distinct data points is around 60%, right? 60-something%. Whereas if you use batching, you divide the data at least into half, so at most you get 50%. And so just from this intuitive argument, it's believable that probably cheap resample is better. And just lastly, you could actually also do the cheap version of subsampling, and this might be related to Peter's question a bit earlier. So subsampling means when you do the bootstrap, you don't use the entire full data set size, but you only resample to get a data size that is smaller. And there are some benefits for doing that. One of them is actually about computation again. So perhaps for some problems, if you have a smaller data size, when you try to do the model fitting, it's actually easier. Okay? But there are actually more benefits than that. So in this case, you could also construct a cheap bootstrap interval where the adjustment here is there is an additional scaling factor in front of the S, where the scaling factor is the ratio of the subsample. So subsample size versus the full data size. And the argument for this is actually very similar to the argument I make for the full bootstrap, full chip bootstrap interval. Okay, so I think I'm going to stop here. So what I introduce is a bootstrap procedure that can use number of resample as low as 1. The theory has asymptotic exactness guarantee, and this is thanks to the asymptotic independence and the normality of the resample and the point estimate. It has a t statistic limit, so you can actually do accurate expansion, but it requires the theory on t statistic. And lastly, there's a question of B and R. I haven't quite answered Jamal's question, but this is something that perhaps we can do soon. So I'm going to end here. Thank you.
Thank you for a very interesting talk. Can we do formal time for questions? Sure. And
Well,
Shane.
of course I'm going to.
Sure, go ahead.
So there's this, like you pointed out, this parallel with the batching literature where they say 20 batches is enough. And in that context, it's enough because the t-statistics are super close to the normal. That's the only inflation factor that's going on. Is that the only inflation factor that's going on in your work as well? Is that?
You mean comparing the batching, right? With and you are talking about the address expansion coefficient.
Yeah, because,
Justification. Yeah.
well, sorry, yeah.
Yeah. So that actually comes from the fact that for batching, there is intrinsic trade-off going on about the number of batches versus the number of data in each batch. So if you have a budget of data size, you can only do so much about batching, right? The thing is, for cheap bootstrap, you don't need that. So that actually released that constraint. And the reason why there is a square in, a square power of k in that coefficient is just because with a fixed data size, if you increase the batch number, there is a decrease of data per batch, and it kind of shows up in that coefficient. And so I think it is, I would be very confident to say a statement that says when the batch size grows, the batching method is going to fail. Because then the number of data in each batch is extremely small, so yeah.
But that you showed us non-overlapping batch means.
Yeah. Yeah, that's actually, I do write overlapping batching in the slide, but I didn't really pinpoint it. And the reason is because, yes, I think it is very similar to overlapping batching. And in fact, I would be curious to see a comparison between what is here in this talk versus that.
Yeah.
But I would say one good thing about using Bootstrap is for the overlapping batching, there are some parameters that you kind of have to play with. For this cheap Bootstrap, whatever computation you have, you just use it, right? Mm-hmm. You just keep increasing your B. So this flexibility is probably quite convenient. Yeah.
So we follow this subject, this batching thing. So often the problem arises for the Markov chain estimating stationary quantity.
Yeah.
So these are intrinsically all coming from Markov chain. Does your bootstrapping things also fit into that setting as well?
Yeah, that's a very good point. I thought about that, but for now, I think the theory here is only for IID. It is true that for batching method, one prominent application is when you have dependent data.
Right.
So I would foresee that we could probably generalize some of this to the dependent case, but we haven't done that yet. So for now, if you have a dependent data, yes, batching I think would win.
All right. So that for this Markov chain kind of problem, still using batching method, right? The
Yes.
resampling, this thing is still down the horizon. Yeah.
Yes.
Okay.
Yes. Yes.
So, is there any idea on how, by adding this extra term from the Edgeworth expansion, how you can reduce the inflation of your interval?
I see what you mean. So it's like a parallel to the standard bootstrap procedure where you do some tricks to remove the first order term for that.
Yeah.
So I thought about that too. So the thing is, I think in the standard bootstrap case, you have this procedure like studentization or iterated bootstrap. But if I use those, first of all, I couldn't maintain the low computation budget. So that's a bottleneck I have. In principle, you could probably do that too here, but then it would require you to increase your computation effort, which is, kind of attacking the whole motivation for this at the beginning. But yeah, I think that might require, it will be an interesting thing to look at.
Yeah. Okay, then let's thank our speaker again for